Unit 8 Review. The purpose of this video is to review the topics that are included in Unit 8. The topics are plane stress transformation, plane strain transformation, and the application of the generalized Hooke's law equations. Use the times shown to jump to a specific topic. The stress transformation we consider in this class is plane stress transformation. In plane stress transformation, all the stresses occurring at a point in a structure can be shown on a planar stress element, like the one shown. Note that there are only three possible stresses: two perpendicular normal stresses, shown here as x and y direction stresses, and a single shear stress, shown here as acting in the xy plane. Note that all stresses are in static equilibrium. For the shear stress, this means that all four sides of the element feel the same magnitude stress. In reality, we live in a three-dimensional universe, and a stress element has thickness into the screen. Here's a representation of a 3D stress element with all possible stresses shown. Note that it has an additional normal stress in the z direction and two additional shear stresses in the xz and yz planes. When the z-directional normal stress and shear stresses with components in the z direction are zero, which is a common occurrence, the 3D element is equivalent to the plane stress element. Now I will discuss why stress transformation is useful. I will use two examples to help. First, consider this pressurized tank. It is fabricated by welding two end caps to the cylindrical body. The cylinder is made by helically winding a metal sheet and welding the edges. The welds are oriented at some angle phi to the longitudinal axis of the cylinder. Now suppose that I want to determine the stress on the helical weld. I would like to know both the normal stress pulling perpendicular to the weld and the shear stress acting parallel to the weld. Our mechanics of materials theoretical equations are limited here. We have formulas for the normal stresses acting circumferentially and longitudinally at a point on the cylinder. But these stresses are not in the direction that we want. However, using the plane stress transformation equations, I can take the state of stress that occurs in one orientation of the stress element and transform it to the state of stress that occurs on the element rotated in the plane. In other words, I can start with the hoop and axial stresses and transform them to the normal and shear stresses acting on the weld. Now consider the second example. Here is a section of an axle that is loaded with a normal force, a torque, and a transverse load. Suppose you are concerned about material failure at the midpoint, where the bending moment is most severe. When we slice the member at the midpoint, we find that there is an internal normal force, internal torque, internal shear force, and a bending moment about the z-axis acting on the cross-section. Suppose we want to look at the bottom of the cross-section, where the tension stress will be most severe. A stress element at this point will look like this. We see normal stress in tension with both the normal force and bending moment contributing. We also will have shear stress on the element caused by the torque. Note that this is a condition of plane stress in the xz plane, which I show on a plane stress element. For determining how near a material is to failure, we often want to find the maximum shear stress or maximum normal stress at the point. Because there is both normal stress and shear stress occurring simultaneously at this point, we can know that the value we found for shear stress is not the maximum value, and the value for normal stress is not the maximum value at this point. Instead, I may want to find the max in plane or absolute maximum shear stress. This value is often used for evaluating potential failure in ductile materials. I may want to find the principal stresses, which are the maximum normal stresses. These values are used for evaluating potential failure in brittle materials. The maximum stress values occur on planes other than the one shown by our initial stress element. We can start with the values on our stress element, which we found using our mechanics of materials equations, and then transform them to find the maximum stress values. Now, let's look at the general plane stress transformation equations. There are 3 equations, 2 for normal stress and 1 for shear stress. There are 4 variables in each equation: 3 stresses, sigma x, sigma y, and tau xy, and an angle theta. The 3 input stresses represent the state of stress on a given plane stress element at some orientation defined by x and y axes. The typical sign convention is that for normal stresses, tension is positive and compression is negative. The normal stresses are shown as positive on the stress element shown. For shear stress, tau xy is considered positive in the orientation shown on the stress element. Note that on the x direction face, the shear arrow points counterclockwise, and on the y direction face, the shear arrow points clockwise. The angle theta in the general plane stress transformation equations represents the angle of the desired rotated stress relative to the x or y axis, depending on the normal stress transformation equation used. To find normal stress at some arbitrary direction in the xy plane, use the sigma x prime or the sigma y prime equation. For the sigma x prime equation, theta is measured from the x-axis. For the sigma y prime equation, theta is measured from the y-axis. To find shear stress on some arbitrary plane rotated about the z-axis, use the tau x prime y prime equation. Take the angle theta as the angle between the x-axis and the direction vector normal to the plane on which the shear stress acts. For all equations, the angle theta is taken as positive counterclockwise or negative clockwise. Finding the stresses on an arbitrary plane are the primary use of the general plane stress transformation equations. For example, to find the normal and shear stresses acting on the weld in this pressure vessel, I would use the general transformation equations. My starting stress element would be the element oriented in the direction of the hoop and axial stresses as shown. Note that my value for tau xy is 0. The normal stress on the weld acts perpendicular to the weld plane. I can use either the sigma x prime or the sigma y prime equations to find the stress. However, the angle theta changes depending on the equation I use. If I use the sigma x prime equation, I need to take theta measured from the x-axis of my original element. Here, this would be the angle phi plus an additional 90 degrees. Another option is to measure the angle in the negative direction from the x-axis to the normal stress, which is equal to the angle phi minus 90 degrees. Note that these 2 options are 180 degrees apart, as are the equal and opposite normal stresses. So the addition or subtraction of any multiple of 180 degrees to the angle theta will yield the same normal stress. I can also use the sigma y prime equation to get the normal stress. For sigma y prime, I would take theta from the y-axis to the desired normal stress direction. Here, the angle would be phi. I could also take phi minus 180 degrees, or add or subtract some multiple of 180 degrees. The shear stress acts parallel to the weld plane. I will use the tau x prime y prime equation to find it. The angle theta is the angle between the x-axis and the direction vector normal to the plane on which the shear stress acts. In other words, I would use the same theta as used in the sigma x prime equations. In this example problem, it says, Determine the normal and shear stresses acting on the weld line. We have a pressure vessel with a helical weld. The orientation of the weld line is 70 degrees from the horizontal as shown. We have an internal pressure, internal radius, and wall thickness for the tank. I begin my solution by finding the hoop and axial stress on an element in the tank wall. Here's a stress element showing those stresses. I will say that the axial stress is acting in the x direction and the hoop stress in the y direction. And that gives me my sigma x and sigma y stresses. Note there are no shear stresses on this stress element. Now I want to transform these stresses to the stresses that are acting on the weld line. There'll be a normal stress acting perpendicular to the weld and a shear stress acting parallel to the weld. I'm going to use the general stress transformation equations to find my stresses. I'm going to use a simple figure to help me identify the normal and shear stress directions and the rotation angles that I'm going to need when I use my general transformation equations. So I've shown the weld oriented at an angle of 70 degrees from the horizontal. My normal stress on the weld is going to be perpendicular to the weld line. So this is the orientation of the normal stress. The shear stress is going to be acting parallel to the weld. So here's the orientation of the shear stress. To find the normal stress, I can use either the sigma x prime equation or the sigma y prime equation. Depending on which equation I use, the value for theta will change. Let's consider the sigma x prime equation first. The sigma x prime equation measures theta from the positive x-axis. I know the orientation of the weld relative to the x-axis, it's 70 degrees, so I know that the difference in this small wedge angle between the weld and the y-axis is 20 degrees. Since my normal stress is perpendicular to the weld, then I know the angle between the normal stress and the weld is 90 degrees. Therefore, this angle is 70 degrees, and this angle here is 20 degrees. So the angle theta, as measured from the x-axis to the direction of my normal stress, is going to be positive 20 degrees. That's this angle right here. I always have multiple options for theta. For example, I could measure theta from the positive x-axis to the normal stress acting on the left side of the weld. That angle is going to be in the negative direction, and it's going to be equal to negative 160 degrees. Notice those two angles, possibilities, are 180 degrees apart. That's because the two normal stress arrows are also 180 degrees apart. If I'm going to use the sigma y prime equation, I'm going to measure angle theta from the y-axis. Here's the y-axis, and we see that the angle from the y-axis to the normal stress to the right of the weld is 70 degrees, but in the negative direction. As an alternative, I can measure the angle from the positive y-axis to the normal stress component to the right of the weld. That's going to be positive 110 degrees. So I have four options that I could use to get the same answer. If I input sigma x and sigma y from our starting stress element and either 20 degrees or negative 160 degrees in the sigma x prime equation, I'll get the value for the normal stress. I'll get the same value if I use the sigma y prime equation, except use negative 70 degrees or positive 110 degrees. So in other words, sigma x prime and the sigma y prime equations are interchangeable. Using the sigma x prime equation, I plug in the stress values from our starting state of stress, and I'm going to use the angle theta positive 20 degrees. Notice that makes the second term in the equation be the cosine of 2 times 20, or the cosine of 40 degrees. The same is true with the third term, except it's the sine of 40 degrees. I get that the normal stress is 10.05 ksi. That's our normal stress perpendicular to the weld. For demonstration purposes, I'll also calculate the normal stress using the sigma y prime equation. In the sigma y prime equation, I'll use theta equal to negative 70 degrees. That means in the second and third terms, it'll be the cosine of negative 140 degrees or the sine of negative 140 degrees, and I get the same normal stress that I did before, demonstrating that the two equations do the same thing. They are just measuring theta from different axes, either the x or the y. For the shear stress parallel to the weld, I'm going to use the tau x prime y prime equation. For this equation, the angle theta is measured from the positive x-axis to a line perpendicular to the shear stress I'm looking for. In this case, the normal stress is perpendicular to the shear, so I'll take the angle from the x-axis to the direction of the normal stress. That's going to be 20 degrees. So the tau x prime y prime equation uses the same theta that the sigma x prime equation uses. So I'm going to use theta 20 degrees. I find that the shear stress parallel to the weld is 2.89 ksi. It came out positive, and so did my normal stress. I will use stress elements to visualize the direction of the stresses on the weld. Now the normal stress came out positive, so it is clear that it is just tension pulling on the weld. This is how I visualize the shear stress direction. On the original stress element, a positive shear stress would be pointing counterclockwise on the x face. That x face was rotated positive 20 degrees. So here is the x face oriented parallel to the weld. Since the value for shear stress came out positive, I will show the arrow acting in the counterclockwise direction. If my shear stress had come out negative, I would show the arrow acting in the clockwise direction. And now I have the normal stress and the shear stress acting on the weld plane, shown in the correct directions. And I'm done. The maximum normal stresses at a point in a structure are called the principal stresses. They can be found using the principal stress equation shown. There are always two principal stresses, acting 90 degrees apart, though it is possible for one of them to be zero. Sigma 1 is always the most positive value. It is obtained by adding the two terms in the equation. Sigma 2 is always the most negative value. It is obtained from subtracting the second term from the first. Note that the first term in the equation can be positive or negative, but the second term is always positive. The other equation shown is used to find the angle of rotation to transform a starting stress element to the principal stress state. The P subscript on theta identifies the equation as applying to the principal stress state. An arbitrary stress element is shown. I know that the normal stresses, negative 10 ksi and positive 2 ksi, are not the principal stresses because there is an 8 ksi shear stress present. In the principal stress state, shown below, there are no shear stresses acting. The angle shown, negative 26.6 degrees, is the angle theta p. I can input the angle theta p and the normal and shear stresses of the original element into the general transformation equations to determine which faces of the rotated stress elements are sigma 1 and sigma 2. The maximum in-plane shear stress at a point in a structure can be found using this equation. The term in plane is used to differentiate it from absolute maximum shear stress, which will be discussed a little later. There is only a single value for max in-plane shear stress, and the equation only gives its magnitude, not its direction. The second equation is used to find the rotation angle from the original element to the element in the max shear orientation. The subscript S on theta identifies the equation as applying to max in-plane shear stress. I can input the angle theta s and the normal and shear stresses of the original element into the tau x prime y prime general transformation equation to determine the direction of tau max in plane. An arbitrary stress element is shown. I know that the shear stress, positive 8 ksi, is not the maximum in-plane shear stress because the two normal stresses are not equal. In the max in-plane shear stress state, shown below, all normal stresses are equal in magnitude and sign. These normal stresses are calculated with the average normal stress equation shown. The angle positive 18.4 degrees is theta s. Note that theta s and theta p are always 45 degrees apart. In other words, the principal stress state and the max in-plane shear stress state are always 45 degrees apart. The possible states of stress on an arbitrary plane stress element in a structure can be depicted graphically on a circle called Mohr's circle. To form Mohr's circle, you start with an arbitrary plane stress element. The two orthogonal axes represent the normal stress, horizontal, and shear stress, vertical. It is common to plot the shear axis positive downward, so that the rotation angle directions on the circle match reality. A state of stress at a point in a structure is represented as 2 points, 180 degrees apart on the circle. The x face of the element is plotted as sigma x and tau xy, with their correct signs, positive or negative, using the convention previously described. The y face of the element is plotted as sigma y and negative tau xy. These 2 points are 180 degrees apart on the circle. A straight line connecting the 2 points crosses the sigma axis at the center of the circle, and the center point is the average normal stress. The radius of the circle is equal to the max in-plane shear stress. The principal stresses are at the extreme left and right edges of the circle, which is equal to the average normal stress plus or minus the radius. Sigma 1 is always on the right side and sigma 2 is always on the left side. The angle between the 2 points that represent the element and the horizontal axis is equal to 2 times theta p. The angle between the 2 points that represent the element and the tau max location is equal to 2 times theta s. So angles on Mohr's circle are double angles in reality. This is demonstrated by the 2 points representing the element, which are 180 degrees apart on the circle, but only 90 degrees apart in reality. Mohr's circle is useful for visualizing rotation directions to get to the principal stresses or maximum in-plane shear stresses. Here's Mohr's circle for the stress element used in the previous examples. The stresses on the x and y faces of the element are plotted. The center of the circle is the average normal stress. We can see that when the point representing the y face is rotated in the clockwise direction, it transforms to the first principal stress, as shown in the stress element. Likewise, the point representing the x face is rotated and transforms to the second principal stress, also shown on the element. We see that when the point representing the x face is rotated in the counterclockwise direction, it transforms to the max in-plane shear stress on the positive side of the tau axis. This means that on the rotated element, the rotated x face has shear stress acting in the positive or counterclockwise direction. Similarly, when the point representing the y face is rotated in the counterclockwise direction to the max in-plane shear stress position, it is on the negative side of the tau axis. Thus, the shear stress arrow on the rotated y face of the rotated element is shown in the clockwise direction. While max in-plane shear stress yields the maximum shear stress in the plane of the stress element, absolute maximum shear stress considers all three dimensions of a plane stress element. For computing the absolute maximum shear stress, the principal stresses must first be known. Then, based on the signs of the principal stresses, the absolute maximum shear stress can be calculated using one of the three equations shown. If both principal stresses are positive, the absolute maximum shear stress is equal to sigma 1 divided by 2. If both principal stresses are negative, the absolute maximum shear stress is equal to the absolute value of sigma 2 divided by 2. If the principal stresses have opposite signs, the absolute maximum shear stress is equal to sigma 1 minus sigma 2 divided by 2. In this case, sigma 2 will be negative, so the term sigma 1 minus sigma 2 should yield a value larger than sigma 1. Note that for this case, the absolute max shear stress is equal to the max in-plane shear stress. The origin of these equations is now briefly explained. The absolute maximum shear stress considers the three-dimensional element. For any plane stress element, the principal stress in the z direction is equal to 0. Mohr's circle is then plotted for each plane, xy, xz, and yz. For the xz and yz planes, Mohr's circle will plot through the origin since the third principal stress is 0. Here's an example of the three Mohr's circles, one for each plane, when sigma 1 and sigma 2 are positive. The largest Mohr circle is drawn from sigma 1 to the origin. The absolute maximum shear stress can be found on this circle and is equal to its radius, which is sigma 1 divided by 2. A similar situation occurs when sigma 1 and sigma 2 are both negative, except that the large circle is drawn from sigma 2 to the origin. When sigma 1 and sigma 2 are opposite signs, the circle for the xz and yz planes are inside the circle for the xy plane. Thus, the absolute max shear stress is equal to the max in-plane shear stress. Because stresses and strains are proportional in linear elastic materials, we can transform strains in much the same way we transform stresses. Recall that strains relate to deformations in materials. For example, when an element of material is subjected to tension normal stresses, the material will elongate in the direction of the normal stress. The normal strain, given the symbol epsilon, is calculated as the change in length divided by the original length. When an element of material is subjected to shear stress, the angle between orthogonal lines changes. The change in angle is the shear strain and is represented by the symbol gamma. Here are the plane strain transformation equations. There are equations for finding the in-plane principal strains and maximum in-plane shear strain. There are also corresponding equations for finding rotation angles and average normal strain. The equations are similar to the stress transformation equations, except that the normal stresses, sigma, are replaced with normal strains, epsilon, and shear stress, tau, is replaced by shear strain, gamma, divided by 2. There are also general plane strain transformation equations. Plane strain transformations can also be represented graphically using Mohr's circle. The key differences are that the axes are changed to represent normal strain on the horizontal axis and shear strain on the vertical axis. Note that the vertical axis is gamma divided by 2, and gamma divided by 2 is plotted at all points. Finally, let's look at the generalized form of Hooke's law. Our first introduction to Hooke's law was with the equation shown. It was derived based on the stress-strain diagram for linear elastic materials. It states that the modulus of elasticity of a material is equal to the slope of the linear portion of the stress-strain diagram, or the stress divided by the strain. it can be rewritten to solve for strain. This form of Hooke's law only considers one-directional stress and its corresponding strain. Let's now consider the three-dimensional effects of stress and strain. Here is an element that is subjected to a tension stress in only the x direction. Here is the depiction of the corresponding strain. Note that the normal strain in the x direction is in the positive direction. However, there is also strain in the y and z directions. In these perpendicular directions, the strain is negative. This is because of the universal material property defined by Poisson's ratio, which we considered earlier. The generalized Hooke's law equations, shown here, consider all three dimensions, which includes the strain in the direction of the stress and the Poisson's ratio effects from stresses acting in perpendicular directions. Note that there are three equations, one for strain in each axis direction. These equations assume linear elastic and homogeneous material behavior. Altogether, there are 8 variables in these three equations. With 3 equations, problems with up to 3 unknown variables can be solved. When approaching generalized Hooke's law problems, I recommend that you consider which of the 8 variables you are solving for and which ones you have. Often, some stress or strain variables may be equal to 0 or are equivalent. Recognizing what variables you have will help you plan your approach to the problem. This example problem states, a linear elastic material fits snugly against 3 smooth surfaces of a rigid slot. The material has material properties E, the modulus elasticity, equal to 50 ksi, and nu, Poisson's ratio, equal to 0.38. A surface load, sigma naught, is 2 ksi. We can see the material inside the slot, and the fit is rigid. In other words, there's no gap between the linear elastic material and the walls of the slot. Also, it says that the surfaces of the slot are smooth or frictionless. The applied surface load of 2 ksi is applied parallel to the direction of the slot. We are asked to find the normal stress in the y direction and determine which dimension, x, y, or z, has the largest magnitude strain. We see sigma y is in the direction of the top and bottom of the slot. We see that the applied load is compressing this linear elastic material. The material will want to grow due to Poisson's ratio effects, but is going to be resisted by the top and bottom surfaces of the slot. Therefore, we expect a compressive stress to develop in the y direction. We will use the generalized Hooke's law equations to solve this problem. I recommend starting this problem by considering all the variables that are present in the 3 generalized Hooke's law equations. There are 3 strains, one in the x, y, and z direction. There are 3 normal stresses, one in the x, y, and z directions, and modulus of elasticity and Poisson's ratio. After listing the variables, consider which ones you have and which ones you're trying to find. This seems easy, but it can sometimes be a challenge. We're given the value for modulus of elasticity and nu. They were 50 ksi and 0.38 respectively. We're also given the magnitude of the surface load, sigma naught. Notice that sigma naught is acting in the x direction. There's an equal and opposite load on either side of the linear elastic block. Note that the applied load is causing compression in the block in the x direction. I show that with a negative sign on the stress in the x direction. Now let's consider the strains. Under the applied load, we will expect the linear elastic material to deform. It will certainly deform in the x direction. It will get shorter, but we don't know how much. In the y direction, the material will want to expand, but it is constrained due to the surfaces of the slot. Therefore, the strain in the y direction is going to be 0. We expect there to be strain in the z direction as the material is compressed. Because there is no constraint on the surface of the material, it will be able to grow in the positive z direction. So it will be non-zero strain. One of the things we want to find is which dimension x, y, or z has the largest magnitude strain. Well, we can tell that it's not going to be in the y direction. The strain in the x direction will be negative. The strain in the z direction will be positive. We want to find the largest magnitude. Now let's consider the stresses. There are two other stresses, y and z directions. As the material is compressed and it wants to grow in the y direction, it cannot because it is constrained. Therefore, a compression stress will develop. We don't know what that compression stress is. In the z direction, the material will grow. There is no constraint to prevent that growth. Therefore, it will just grow freely and there will be no stress in the z direction. The only way we would get stress is if something was confining the change in length. So, by looking at our variables, we see that there are 1, 2, 3 unknowns. And we have 3 equations. We have exactly what we need to solve this problem. I'm going to write the strain equations one at a time. And I'd like to start with the equation that has the fewest unknown variables. I think that will be the strain in the y direction. We know the strain in the y direction is equal to 0, so I'll start there. I take the epsilon y equation and I plug in my known values. For E and sigma, the units are KSI. I only have one unknown in this equation, sigma y, and I can solve for it. I find that sigma y is equal to negative 0.76 KSI. As previously stated, we expect the stress in the y direction to be compression as the block pushes against the upper and lower walls of the slot. We have found our first answer. Next, I will solve for the strain in the x and then z directions. I find that the strain in the x direction is negative 0.034. The units cancel out, and if you recall, on strain we can show the units as inches per inch. The negative sign is expected because in the x direction we have a compressive stress acting. So we expect the linear elastic block to get smaller in the x direction, and thus we have a negative sign on our strain. Lastly, I solve the epsilon z equation, and I get that the strain in the z direction is positive 0.21 inches per inch. And again, that is what we expect. As we compress the block of material, it will grow in the only direction it can, and that is in the z direction. So we expect a positive strain. By comparing our strain values in the x, y, and z directions, we see that the strain in the x direction is the maximum magnitude strain, and our problem is complete. This completes the review of the topics in Unit 8.